Bismillahirrahmanirrahim. Assalamu alaikum dear students. I'm Arif and I welcome you all to the next and the last session on the subject of system programming with Linux. Alhamdulillah, all glory to Allah who gave me strength to complete these 40 videos on the subject. Well, since this is the last session on this subject, so I would like to take this opportunity to thank my brother Rauf, whose continuous support has helped me in all spheres of life. I would also like to thank my teacher Mansoor Server, from whom I learn how to teach. To me, he is still a legend in the field of operating system and system programming. Last but not the least, thanks to all my students who are my teachers as well. Well, this slide shows the agenda of today's session, and we are going to finish what we started 2 sessions back, that is exploiting the buffer overflow. Well, first of all, we are going to find and understand the vulnerability in our program. Then we are going to craft an input string such that the control of flow move to some piece of code of our choice within the code section. So let's see how we can do it. Well, this slide shows our vulnerable program named virus.c. The main function over here calls the get input function, which creates a buffer on the stack of size 10 bytes to store the characters given via keyboard using the read system call. And there you see the vulnerability, and that is, instead of reading 10 characters, it is reading up to 1000 characters. Finally, it displays the content, rather the count of the characters read on standard output, and then this return statement will try to bring the flow of execution back to the next instruction of the main function. One more thing to note in this program is that the function named virus is not being called from anywhere in the program. Well, from the knowledge of our video session number 38, this is the layout of the process stack when the control of execution is at this read system call. Observe the layout of the function stack frame of this get input function, particularly the saved return address, which will be containing the address of the next instruction inside the main after the call to the get input function. Also note the space created for this buff, and this buff is of almost 10 bytes if we ignore the alignment space. Also note that the stack grows from higher addresses to lower addresses, but any writing in this buffer will be carried out from this address, lower address, to the higher addresses. Now let us suppose that the user enters some characters, and he or she enters more number of characters than the buffer can handle, and we see that the buffer is overflowing. And finally, the user input may override the saved return address as well. As you can see, the B's has overwritten the return address. Now, if the user has given this input to the program, the number of bytes read by the read system call will of course be displayed on the screen, that is, this line will be executed. And then this get input function will try to return. It will try to return to this corrupted address, which is of course not the address of the next instruction inside the main. Rather, this address might not be a valid address inside the code section, and we get a segmentation violation and the program crash. Now somehow, if I can overwrite this location of stack containing B's with, instead of starting address of this virus function, the flow of execution will transfer to this piece of code when the get input function will execute its return statement. I hope the concept is clear. Now a $100 question is, after how many A's I need to give the address of the virus function? And of course, I also need to find out the starting address of the virus function as well. So this is the expected layout of the input string, and I need to find out the number of A's I need to give, and after that I need to write the address of the virus function, which will come up over here. I need to find out these number of A's, and then I need to find out the address of the virus function. Finally, I will create this input string, and I will give this input string to this program. Fine, enough of concepts. Let us now move on to the Linux terminal and make this happen. Well, you all know that we are working on Kali Linux, and let me show you some information about the platform. The hardware platform is x86 64. Well, x86 64 or AMD 64 means the same thing. This is a 64-bit processor by Advanced Micro Devices. Let me also show you the OS and the kernel version. I'm running Kali Linux 4.9. One more thing we must do before proceeding is to disable the ASLR. Let me check out from the file proc sys kernel randomize vspace. So it contains 0. Normally once you will run this command, you will find a 2 in this file, which means every time you run a program it gets different addresses inside the stack, data and the code section. If you want to disable it, you simply write a 0 in this file. Let me show you the command for that as well. We write a 0, and we need sudo privileges for this. Sys kernel randomize vspace. Okay, fine. Sorry if I'm repeating things from the previous session, but I think this is important. Moreover, I think a teacher is someone who always repeat. Anyway, let's quickly see the code of our program virus.c. So this is the code. Let me compile it with the ggdb flag to include the symbols. And let me create the executable with the name of virus. And let me execute this virus program. Let me give it some A's. And the number of bytes are 6. And let me give it a lot of A's. And of course I get a segmentation violation. Well, since I have to do this task again and again, so let me write a Python script that will generate the input that can be given to this program. Let me show you that Python script exploit1.py. Well, this is a very simple Python script that creates a buffer containing 1000 A's, and then it creates a file named payload1 and write the contents of this buffer in this file. That is great. Let us now run this script so that it create this file payload1. It has created. Let me show you that file payload1. So it contains 1000 A's. Let me be sure that it contains 1000 A's. Well, yes. Now let us pass the contents of this file to our vulnerable program. /virus payload1. Well, this less than sign actually redirects the input of our program to this file, so that the read system call now will not block at the keyboard, rather will read characters from this file. And once we try to execute it, we get a segmentation violation. Fine. Let us start now with our scuba diving business by loading this program in GDB with beta-q, that is in quiet mode, virus. Let me put a break in main. and let me run it with this input. Great. Let me shrink the size a bit. Fine, we are inside the main function. Let me press SI. So this is the call statement, call to the get input function. Let me move ahead. So now we are inside the get input function. Fine. If you note the top of the stack, that is E1C8, contains this address 554766. This is the return address which has been pushed at the top of the stack before calling this function. Now let us keep pressing NI and keep moving ahead inside the get input function. We read the input is read, we do with the printf call, and then finally we reach the ret instruction. Now the top of the stack is E1C8, and you can see the return address, the saved return address, which was 554766, is now corrupted, and it is containing A's, string of A's, instead of the return address to the main function. Okay, let me press SI again, and we get the segmentation violation. Let us see the contents of register RIP. Okay, let me move ahead. Well, this is RIP. RBP of course contains A's, but RIP does not contain A's. So a $100 question is, why on God's earth the ret instruction, that is this instruction, has not executed the pop rip instruction and placed the contents at the top of the stack inside this register? Anyone can try to answer this question? Okay, well, yes, this is because the maximum possible user space address on x86-64 is 0x0000 7FFF FFFF FFFF. So this is the maximum possible address, 4 zeros, 7 and then 11 Fs. While the top of the stack, that is this, contains 16 A's, which is a far bigger address. So that is why operating system is unable to place this address inside the RIP register. Okay, now dear students, our goal is to create a special string which, when given as input to this program, writes the buffer variable on the stack in such a way that this address FFE1C8 should be overwritten with the starting address of the virus function. Let me check out the address of the virus function. pdisassemble virus. Okay, so this is the address of the virus function, 55476D. So if somehow I can write this address over here, so when this ret instruction will be called, this will be popped off from here and placed in RIP, and the control flow of execution will shift to the virus function. So I need to know after how many A's I need to give the address of the virus function in my input string. Let us quit the debugger for the time being. Dear students, there can be more than one ways to find out the answer to this question. Let us use PIDA. PIDA's command pattern create for this purpose. Let me run GDB and let me say pattern underscore create, and let me create a pattern of 1000 bytes. Pattern.txt, pattern.txt. Well, fine. So we have created our debrugen sequence having unique n-length subsequences at any of its points. You can view this pattern.txt. Well, this is the sequence. Now let us load this the vulnerable program in GDB again. file./virus. Let me put a break in main again, and let me now give this input string as input to our vulnerable program. Good. Let us press SI, call the get input function. You see the top of the stack E1C8 contains the return address, which is the valid address to the main. Let me execute the get input function, execute the read call, note the state of the stack after this read. So we have the input over here. Let me shrink the size again. Let me keep pressing NI and move to the ret instruction. So we are at the ret instruction inside the get input function, and now you see at the top of the stack we have these bytes: A opening bracket double A D double A. So these are the 8 bytes stored over here, while the next contains semicolon double A closing bracket double A and so on. So if I press SI again, the ret instruction will execute, the contents of the top of the stack will be popped, and that is of course not possible because that is an invalid address, so we get segmentation violation error. Now let us find the offset of this substring. Let me copy this and let me use the pdas command pattern underscore offset. Let me give it this string, and there you go. The offset is 22. Great. Okay, so we have found the offset in our input string, after which the next 8 bytes will override the saved return address on stack. Let me quit, increase the size a bit, and now we need to create another Python script which when executes will generate an input string to be given to our program. For this purpose, to save time again, I have already written it, and that is exploit2.py. Okay, so this struct is a Python module used to interpret strings as packed binary data. Over here I have placed 22 A's, and after 22 A's I am placing this address onto the buffer. Either you can use this way or you can use the pack function. Well, you can manually create the 8 bytes address in little endian with the most significant 16 bits containing zeros, and the rest 48 bits containing B's, and you know the corresponding ASCII representation of P is 42. We can do the same using the pack, which is used to generate a null signed 64-bit little endian value, and this format string over here, this less than sign means little endian, and this Q means 8 bytes integer. So whatever suits you. And after that I have placed again 70 A's. I've created the file. Let me run this script to generate our payload. Python exploit2.py. Let us view the contents of the file payload2. Payload2. These are the contents. You can see 22 A's, and then we have 6 B's. Okay, let me show you in some hex editor. Let me use hex curse. Payload2. Okay. Over here we have 2 panes. On the left we have the grid representation of file in hex format. You can see it over here. On the right you have the ASCII text representation. You can use arrow keys to move left and right, and of course you can use tab to shift to the other pane. And you see over here we have these 8 bytes in little endian, of course. And of course, since this is an editor, so you can edit it as well. You can do Control plus S to save and Control Q to exit. Let me press Control X. Well, I think since we only wanted to view the content, so we could have used the hex dump as well, which would have been better. Hex dump payload 2. So this is it. Once again, you can see this is the 8 bytes address. The most significant 16 bits are 0. Let us not detract from our objective, and let us load our vulnerable program and pass this input to it. gdb-q ./virus, put a break on main, and let me run payload 2. Okay, so we are again at the main. Let me press SI. We call the get input function. Let me press again. Top of the stack E1C8 contains the return address to the main function. Let us execute the get input function by pressing NI again and again. We read the input and then we print that input. And finally we reach the ret instruction. And once we reach the ret instruction of get input function, you see the top of the stack contains this address, 6Ps. This is a very valid address, and this address of course can be moved to this RIP. If I press SI again, you see the RIP now is containing this address, which is of course a valid address that can be placed in RIP. But of course this is not a valid address in the sense that it does not point to the code section. So once our program will try to execute the instruction residing at this address, we will of course get a segmentation violation. There it is. Okay, now the final task is that we need to replace these 6 B's in our input string with the starting address of the virus function. Let me check the address again. pdisassemble virus. Let me copy this address, and that is 55476D. Let me quit the debugger. Let us rewrite our final Python script that will generate our final payload. Once again, to save time, I have written the Python script exploit3.py, and the only difference is we just have changed the address. After these first 22 A's, I have written the address of this location over here. Let us run this script exploit3.py to generate the file. Let me show you the contents of this file. Payload 3, and there you go. So this is the address of the virus function where I'm going to shift. Let me load my program in GDB again, in quiet mode, run it with the input of payload 3, and there you go. Our virus function has executed. Let us hack planet Earth with Arif. Okay, so we have successfully run this inside the GDB. Let me try it running outside GDB. Let me say cat payload 3. Let me pipe it to virus, and there you go. Great. So dear students, whenever we will give this carefully crafted string as input to this vulnerable program, it will execute the function that is never called from within the program. Let us fall back to slides and see what is next. So we are done with part 1. In part 2, we will simply extend the same example by writing the shell code craft the input string again, inject the shellcode, and test it both inside and outside the debugger. Well, this is the same piece of code, the same function stack frame of get input function, but this time the input function input string will be a bit different. We have about 22 no operation instructions that does nothing. On x86 its opcode is hex 90. Then we have address of our shellcode, that is the next higher address, stack address. After that we have our shellcode. So we will override this address with this address. Let me show you this. We will give the input, it will keep overwriting it, and after 22 not operation instructions we will write this location. Instead of B's we will overwrite it with the address of this place, and over here we have our shellcode. So when this get input function will return, instead of returning to the main function or maybe the virus function as we have seen before inside the code section, it will return to our shellcode residing on the stack, and we'll try to execute this. And keep in mind that for this to work, the stack must be executable, and we must also disable the stack canary protection. One more issue that may occur is due to a bit of alignment issues, or maybe due to some additional environment variables. That the addresses may change a little bit. So it is recommended to place nop sled after this next location address and before this shellcode, like this. So to handle this issue, we place this, so the control transfer to this place, and it keeps on shifting, doing nothing, and finally it reaches our shellcode. So this is known as a nop sled. We need to create or craft this input string now. Let's once again move to the Kali terminal for the proof of the concept. This is the same program which we are running, and of course this time we need to compile it using this command, because we want to make the stack executable, and we also want to disable the protection mechanism of Canaries. Fine. Let me load it in the debugger again and put a break on main, and let us run it with the same payload 3 just to confirm the stack addresses where return address is saved. Let me run it with payload 3 again. Let me press SI, and you see the top of the stack is the same address E1C8, which contains this. And this time we need to override this place with the next address of the stack, that is I want to store E1D0 over here. So when get input function returns control, the transfer of execution moves to this place, and over here I will be having my shellcode. Let us quit the debugger, clear screen, and write another Python script that will craft our input string for this purpose. And once again I have written that Python script. Okay, so we need to import the pun tools as well, and I am setting the architecture to AMD 64 and the OS to Linux. Well, you can use the shellcraft submodule of puntools to generate the shellcode, or you can just download the appropriate shellcode from maybe the shellstorm.org. Well, this is the basic shellcode of a shell. And of course, we discussed the generation of shellcode in detail in previous session. So if you are confused over here, please do watch that. And finally, you see over here, we have replaced the address with FFE1D0. This is the next higher address of the stack where the return address is saved. So we have 22 no operation instruction, then we have the address, and then I have a bit of no operations again, and then we have the shellcode. So I think that makes sense. Let us save and exit. Run Python exploit 4.py, generated the payload 4 file. Let me show you hexdump -c payload 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 4. So this is the file which contains the payload, and of course you can see this is the address FFE1D0, and then after that again I have about 8 no operation instruction, and this is our shellcode starting from 6A205. So once the get input function will return, it will return the control to this address, and over here we have our shellcode. So I think this is again making sense. Let us now run our vulnerable program in GDB and give it this input, gdb-q./virus, and let me, without putting a break, give it this input, and let me run it, and there you go. You have successfully created or spawned a shell, bin dash, and of course bin dash is a soft link to bin-sh. Let me quit now from here, and let us try to run our vulnerable program outside GDB and give it the same input. Let me say cat payload 4./virus, and we get segmentation violation. It runs perfectly fine inside GDB, but it is not working outside GDB. Well, dear students, one possible reason for this is GDB adds some additional environment variables other than the ones that it gets from the parent shell. Let me confirm this to you. If I see the environment variables using E and V, so these are the environment variables, and of course these are there on the stack. And let me run GDB and check the environment variables again. Show env, and over here you see there are these 2 additional variables which were not there inside the main, inside the parent shell, that is the lines and the columns. So these environment variables reside of course at the very top of the stack in the function stack frame of the main, so they are going to affect all the addresses. Well, dear students, one solution to this problem is inside GDB, before you craft the input string, delete all the environment variables. That is, you do unset env to remove all the variables. You don't have any variables now. And now when you run your vulnerable program outside GDB, you precede the program name with env- to unset all the environment variables. So this is one solution. Another solution is you use the NOP sleds, no operations. There are 2 variables you can adjust to fix the issue. You gradually increase the jump address, and you increase the size of the NOP sled preceding the shellcode. Okay, let me quit, and let me show you the 2 exploit, gedit exploit 4 and exploit 5. So this is the exploit4 file which works perfectly fine inside the GDB. What I need to do is I need to increase this address, and I need to increase these no operation instruction. You can increase them by 20, then finally you will come across at a setting where this program will certainly run outside GDB, and I have done it. And the file is exploit5.py. You see the only difference between these two files is the address over here is E1D0, which works inside GDB, and the address over here in exploit 5 is E2D0, about 256 bytes ahead. And in exploit 4 we have just 8 no operation instruction after this address and before the shellcode, while over here we have 200 no operation instruction. Let me generate the new payload by running this script, python exploit5.py, and let me show you hex dump -c payload 5, and this is the payload. You can see the 22 no operation instruction, and then we have the address, and that is E2D0, and after that again I have about 200 nops led, and then I have my shellcode over here. Let us now run our vulnerable program outside GDB with this payload. Get payload 5, pipe it to virus. Great. It has successfully executed, but the shell shuts off instantly because the shell isn't waiting for an input. So let me run it with hyphen over here. The hyphen ensures that the virus program now gets the input from this file, plus it will wait for the input to be typed via keyboard as well. Let me press enter. Now this is a new shell. Let me type the command who am I am Arif. Let me say ls, it executes the ls command. Let me say pwd, it executes the pwd command, and let me do exit. Great job done. So we have successfully exploited the vulnerable program virus and have got a local shell on this machine. Dear students, for achieving escalated privileges, let us change the ownership of this program to root. Sudo chown root virus, and let me set its SUID bit as well. Sudo chmod plus s virus, and now let me run this program again. And now when I say who am I, you see I am root now. And let me show you the file containing passwords shadow, and let me just grab the record of Kakamanna. You see, this is the record of Kakamanna containing his password. Let me exit. Great, really great. Well, dear students, for completeness, let me show one more thing, and that is to place the shellcode in some environment variable. Instead of placing it on the stack after within the input string, let me place it in some environment variable. Let me get the address of the environment variable, and on return from get input function, shift control to the address of that environment variable containing our shellcode. Okay, so let me clear screen, and let me first create that variable. Export my shellcode. Let me name it my shellcode, and let me say python-c print, and let me put the shellcode over here. I have the shellcode with me, and it is inside the file my shellcode.txt. So this is the shellcode. Let me copy this shellcode from here. You can use any shellcode which you can get from the Shellcode-storm website, or you can write your own. Let me show you echo dollar my shell code, and this is a shell code. And if I see env, you can see we have the shellcode environment variable over there. Now what I need to do is I need to find out the address of this environment variable whenever a program will be loaded. Since I have exported this environment variable, this variable will be given to the child process, and it will of course will have some address. We can see that address from GDB as well, but let me show you a program, get env_addr.c, which uses a system called get env, and this get env system called simply display the address of this variable, and I don't think that this line is really necessary. We have seen get env in our previous sessions. Let me compile this program, get env_addr.c. Let me run it, and let me give it the name of the variable my shellcode, and this is the address FFEE53. Okay, so what I need to do is I just need to use this address over here. So after the 22 no operation instruction, I am going to place this address. So when the get input function will return, it will return to this address, and this is the address of the environment variable residing on the stack containing the shellcode, and I think it should execute. Let me use Python exploit 6.py to generate payload 6, and let me show you the run of this using cat payload 6, put a hyphen over here, a pipe and a virus, and there you go. Let me put ls, and it gives you the listing of the present working directory, pwd, who am I, and I am root, because the SUID bit of this virus is set and it is owned by root. Let me show you this. You see, this is the virus executable, owner is root, and the SUID bit is set. That is great. That is great. Let me exit from this. Let us fall back to slides again. Okay, finally we have the home task, and the first task is, dear students, I have uploaded an executable which is a vulnerable eco server program on the Bitbucket account. Please carry out the vulnerability analysis, craft the input string, and inject the shell code that will perform the following task: TCP bind shell creation or TCP reverse shell creation. And we have discussed these two in our previous session as well. Well, dear students, we have done this buffer overflow exploit by making the stack executable. The question is, what if the stack is non-executable? Can we still exploit the buffer overflow vulnerability? Well, dear students, try doing that by digging out details about a class of attacks known as return to libc, also known as return-oriented programming, ROP. And another option to bypass this security mitigation technique is by using the mprotect system call, which can be used to change the access protections for the calling process memory page containing the stack. Well, to carry out the vulnerability research and to craft our input string, we have disabled ASLR. Can you think of doing all this with ASLR enabled, which is the default on most of the modern operating systems? Well, brute forcing, NOP sleds, restrict entropy, and information leak are some of the options discussed in literature. Please dig out these concepts if you have interest in this domain. Finally, we have done all this by telling the compiler not to use the stack canaries. Do search out options that you can use to override this protection mechanism as well. Okay, dear students, so that is the end of this session as well as the end of this course, System Programming with Linux. Well, these last 3 sessions are actually an intro to my maybe upcoming course on the subject of hacking planet Earth with Arif. Hope you all have enjoyed learning the system programming course with me as much as I did enjoy making it. See you in some next course. Take care, happy learning, and Allah Hafiz.